This is a new exercise. Again, it's from Bristol University. It's an exam question. And the hypothesis is that the limit of an equals to plus infinity. So, an is a sequence of positive numbers, as you see here. An is a sequence of positive numbers. And we have to prove that under this hypothesis the series an plus 1 over an diverges. So I want to prove that, and I will suppose that it isn't valid. So suppose that the series an plus 1 over an converges. Then I remember a proposition that says that if the series an converges, then the limit of the sequence an equals to 0. So, since the sum converges, then the limit of an plus 1 over an when n tends to infinity must be 0. Now, we will use the epsilon definition of the limit. And what does this mean here? That there exists an n capital such that for each n small that's greater or equal than n capital, we have an plus 1 over an less than epsilon for each value of epsilon. So, as you remember, this is the epsilon definition of limit. Now, this is valid for each value of epsilon, so let's take epsilon equal to 1. So, for epsilon equal to 1, we have that there exists an n such that for each n small greater than n capital, we have an plus 1 over an less than 1. Now, if you want to see that a little better, so geometrically, take the straight line here, and on the straight line you have n, that here, then you have n plus 1, n plus 2, and n small, because as you see n small is greater or equal than n capital. So n capital is here and n small is here. Now, since this relation is valid for n equals n capital, everything I'm writing here is valid. So an plus 1 over an is less than 1. An plus 2 over an plus 1 is less than 1. And an plus 1 over an is less than 1. Each of these relations here is valid. Now, I'm practicing here a somewhat strange algebraic manipulation. I'm taking an, so the general term of the sequence for the index n. Don't forget that the index n is greater than n capital. And I have here an equals an over an minus 1, an minus 1 over an minus 2, an plus 1 over an times an. As you see, what I'm writing here is totally valid, because if you cancel these couples here, you will find an equals an, and that's true. But now, as you see here, each one of these ratios here is less than 1 is less than 1 is less than 1. So I can say that for each n greater than n capital, I have an less or equal than an capital. Now, what I see here actually is that if I again take the numbers here, this is an capital and this is an, okay, an equals to an, of course. An plus 1 is less or equal than an plus 2 is less or equal than an. So every term of the sequence from an capital on is less or equal to an. So all the terms of the sequence an here are less than an capital. Outside this interval here we have the terms a1, a2 up to an minus 1. Now all the terms of the sequence from an capital and on are included in that interval. I have only a finite set of terms outside that interval, and these are these terms. Now, some of these terms is the maximum one. So take as L the maximum of a1, an minus 1, an. This maximum term is somewhere here, maybe it's an also. So what I found is that an is less than L for each value of n belonging to the natural numbers. So my sequence an is bounded. But hypothesis said that limit of an is plus infinity. So from these two I get a contradiction. Why did I get a contradiction here? Because I supposed that this series converges. So the result is that this series doesn't converge, and in that case you can say that it diverges. That's what I wanted to prove.